we defined fractions last week. And so I wanna, okay, suppose there are 3 friends and they're about to split a pizza evenly, right? So suppose this is our slice here. What fraction could express our share of the food?
1/3 each.
Yes, very good. 1/3. Okay. And we are just about to start eating when 3 other friends arrive. So we're gonna be nice and we're gonna share. So here is what's gonna happen. Each of us will split their slice into two halves. And now, before we give it to our friend, this is what we see on our plate. What fraction could express this?
2/6.
Yes. And so 2 fractions are equal to each other if they represent the same amount of pizza. They're also called equivalent fractions. And so a fundamental property of fractions is that you don't change the value of a fraction if you multiply upstairs and downstairs by the same number. That would be just splitting the slices further. And because equal signs work both ways, you can also divide both upstairs and downstairs by the same number. So 1/3 equals to 2/6. Well, what happened, and you understand why. We doubled our share and we doubled all the shares. But if 6 more friends arrive, then we can trisect our share, right? We can split every big slice into 3 pieces instead of 2. Then what fraction would we get? Still just this. If we don't, so forget the dotted lines and we split it into 3 equal parts, right? So we split each slice into 3 equal slices, and we're still looking at this part. What fraction could express this now? This is 3/9. And so you can divide both upstairs and downstairs because equal signs, you can travel along them back and forth. So the next thing is then, okay, for the mental health of math teachers, what if 30 people turn in 30 different answers? Say the answer is 1/3, but one person turns in 2/6, another person turns in 3/9, another turns it. There are infinitely many versions that we can make, right? You just take the numbers 2, 3, 4, 5, and you just multiply upstairs and downstairs. So that was with 2, 3, 4, with 5. Hit upstairs and downstairs by 5, you get 5/15, right? So we should somehow designate one form as the one that we turn in like nicely. And that's the simplest possible form, and that kind of makes sense. If you can write something as 1/3, perhaps we shouldn't write it as 5/15. It's the same thing, so why not the simplest one? So this form, when you can no longer divide upstairs and downstairs by anything, because they don't share anything common, that is called simplified or reduced or in lowest terms. So those are the same thing. And so we often are gonna simplify when it's the final answer. For example, can you write 80% as a reduced fraction? Write it as a fraction and then start knocking out things that are common until you can no longer do that, right? 80% is just 80/100. And now we can divide upstairs and downstairs by the same thing. And you don't have to get it right the first time. You can see just a 10, right? They both end in a 0, so we can chop off 1 0, then we get 8/10, but that's not reduced yet, right? Because they're both even. 4/5, exactly. So 80% as a reduced fraction is 4/5. But let's do it backwards. How about, can you write 3/25 as a percent? I give you nice numbers. Look at the denominator. We need 100 instead of 25, but 25 is a divisor of 100. You can scale this up to 100, so you don't need to divide at all. Multiply upstairs and downstairs of this fraction so that the denominator becomes 100. What number would do that?
4.
Yeah, so we're gonna hit upstairs and downstairs by 4. And 12/100 is 12%. That's what it means. So we can go back and forth between the two forms. We can also, any questions so far? So I'll just give you two more. So 60% as a reduced fraction, please, and 2/5 as a percent. All right.
60% should come out to 3/5.
Yes. Oh, yes. So 60% is 60/100. And when we divide by 20, we get 3/5. Very good. And then 2/5 turns out to be what percent?
I got 40%.
Yeah, me too. We hit both upstairs and downstairs by 20. Again, so format, because format is important. The thing with algebra is whatever is on the paper, you don't have to keep it in your head. And so you will not need to, you will remember that 5 seconds what you're gonna do. But if you wanna multiply upstairs and downstairs by 20, just don't do this. Because that's reserved for something else. If you must, just do this, 2/5, and then you times 20 times. That will work. But I think eventually you will not need that. Sometimes less is more. I think this is readable. But I'm used to this. Those are readable. That's a subjective term. It's outside of the jurisdiction of mathematics. Any questions? All right, before we move on to our last topic, I wanna point out something and show you an example. Every division can be viewed as a fraction, and every fraction can be viewed as a division. There is a duality, fraction and division. They are one and the same thing. And that can be exploited. You can use this fact. For example, I wanna show you how I divide by 5 in my head, or before I'm a little senile now. So let's say we're gonna divide 120 by 5. And I don't like dividing by 5. So this is a division problem, but for a split second, I'm gonna think of it as a fraction. And I'm gonna double upstairs and downstairs because I really like to divide by 10. So if you double upstairs and downstairs, and now this division, you can do it in your head, right? It's 24. So this is an example of when you look at the division and for a while you use it as a fraction. I grew up with calculators, but the generation before me, they didn't have calculators. They were middle-aged by the time calculators come. They have thousands and thousands of tricks like this because they had to do everything without calculator. So I just wanted to show you this one. All right, any questions?
So we just have to remember, whatever we do to the top number, we must do the same thing to the bottom number.
And it has to be multiplication division. It cannot be add the same amount. So it has to be, I refer it to scaling, like you scale up. It's like a recipe, right? If the recipe calls 2 cups of sugar for 6 people, which that's a lot of sugar, say 2 cups of, let's say flour, although I'm not sure I can spell it, for 6 person. And you have 12 people coming, then how many cups do you need if you want to bake for 12 people?
For 6 people, you multiply that by 2.
Exactly, instead of adding 4, right? So it's multiplicative. Right. You can scale it up, scale it down. If there are 60 people, you need 20 cups. And that's exactly what's going on. This is, I could say per, and then it's literally division. And yeah, that per means division.
I got a question.
Okay.
Multiplication, division. Is it because of the order of operations that those two behave the same?
No, it's because the definition of fractions is multiplication, division, right? Grab something. Remember how we define 3/5? Good question, by the way. 3/5 was take something, divide it into 5 equal shares. and then take 3 such things. So you divide and then multiply, right? So 3/5 of 60, well, 1/5 would be 12. So there is a division. And then we take 3 such slices and we get 36. 3/5 of 60 is 36. So the definition itself is multiplicative, multiplication division, which is why it will not work at all with addition subtraction. And that's the same reason why exponents behave very well with respect to multiplication division, but not addition subtraction, because the definition itself is repeated multiplication.
Oh, so that's why in order to remove the lower part of a fraction, you multiply it by whatever that number the lower part of the fraction is.
I'm not
In
sure.
case in point,
Give me an example.
we had x plus 10 over 2 earlier.
Oh. Yes, but I was talking about division there. X
yeah,
plus
but
10.
you got rid of the 2 by multiplying by 2.
But that is doubling it. Here we're multiplying upstairs and downstairs by 2, which means we're really multiplying it by 1.
Okay, all right.
But yeah, it's good. Yeah, I'm mixing things. I'm trying to hurry up because starting from scratch is very difficult, but I think it's a good idea. So yeah, this is undoing a division. But while we're at it, so we also do something, we can scale up to compare things. So say we wanna compare 3/5 and sorry, 4/7. Now they both are more than half. I think you probably have a feel for it. And you can already compare these by taking something that's divisible both 5 and 7, and you evaluate what's 3/5 of, let's say 70, and what's 4/7 of 70. And then we compare the results, right? What is 3/5 of 70?
It's 70 is 7.5, 6, 12. It's 18.
No, but I'm glad you're playing. I'm getting
42.
42, yeah. When you divide by 5, you get 14, and then 3 times 14 is 42. Anyone here reads Douglas Adams? 42? No, okay. And then when we take 4/7 of 70, 1/7 is 10, and 4 of them is 4 times 10.
40.
So which one is better if you want more?
3/5 of 70.
Right, 3/5 is a bigger share. But see, here is the problem. This is 3 slices, this is 4 slices, but these are smaller slices, right? Because this describes the slice as, well, 7 equal makes up a whole. So if someone says, okay, work for me, and when you make $5, I give you 3 out of every 5, and the other guy says, I'll give you 4 out of every $7 you make. Which one is a better deal? Well, 3 out of 4 is more than 3, but you have to work more for it. So we cannot really compare them. This is one neat way to compare them. Turns out 3/5 is slightly better, not a lot better, but slightly better than 4/7. But we can also compare it now with the fundamental property of fractions, just scaling it up to what we call a common denominator. So what if we multiplied upstairs and downstairs of this number and upstairs and downstairs of this number, so that we bring them to a common denominator, which has to be a common multiple, which is actually not 70. What is the, and that's another topic we're not going to be able to finish today, is what is the least common multiple of 5 and 7?
35.
Yes. So if we could rewrite both of them with the same denominator, then we can compare them.
21 over 35.
Yes, 5 to 35, that was 7. 3 times 7 is 21. And 7 to 35, that's 5. 4 times 5 is 20. And then you compare 21 out of 35, only 20 out of 35. So this is another way of comparing fractions. And later on, when we're going to add, well, how do we add things with the same denominator? What would be 3 over 5 plus 1 over 5? Well, if you think slices, 3 slices and another slice, we add it together, all together, there are 4 slices, right? So it's very simple how we add fractions with the same denominator. And how do we add fractions with different denominator? We don't. So if we have to add 3 over 5 and 4 over 7, we cannot do that. We have to bring them to a common denominator, and then you can add the slices. You have to talk about the same size of slices before you can count them. So this would be 3 over 5. So you diagnose first 35, and then 5 to 35, that was 7. 3 times 7 is 21. 7 to 35, that's 5. 4 times 5 is 20. And now that they have the common denominator, we can add the top. I should have used a better example. All right. So, but that's in the future. We're not going to add and subtract them yet. That's next week, the week after. But what did come up here is the least common multiple.